All right, let's begin our review of radicals and also rational exponents. Um, on the right hand side of the screen, you'll see a list of square roots. These are perfect square roots. And the answer to the right of them. We're going to refer back to these. So first we start out with what is a square root? Well, square root should look something like this. It may have a number or maybe sometimes a variable, maybe a variable with an exponent underneath the radical symbol. So we have the radical symbol. Um, we can write the square root of 64 like that, or we can write it with the 2 right there. When there's nothing there, is actually implied to be an invisible 2. So this is known as the index, that number there. Again, when there's nothing there, there's implied to be an invisible 2 in that index. Um, this number underneath the radical symbol is known as the radicand. Um, I don't think it's mentioned too much, that term, but I wanted to introduce it to you. And then, of course, we have the radical symbol. So I called it a square root just a few seconds ago, and it's a square root because we're taking the second root of 64. If we had a 3 in the index, I would call it the cube root or the third root. If there's a 4 in the index, we are taking the fourth root, right? So we're taking the second root, and a lot of times people call the second root of some value the square root. All right, so to get the square root of 64, since there's an invisible 2 there, we're basically saying what number times itself twice will get us 64, right? If I was taking the fourth root of something, I would say what number times itself 4 times will get us 64, right? So I'm not saying times 2, I'm saying times itself, what number times itself. And if you and I think about this, we would come to the conclusion that 8 twice, right? 8 twice times itself is equal to 64. And so therefore the square root of 64 is equal to 8. And you can see it there in our chart. The square root of 64 is an 8. So we can do the same thing for all of these numbers. For instance, this last one, the square root of 225, we're thinking what is the largest, we're thinking what number times itself will make 225, and that'll be 15. 15 times 15. All right, so let's go further. Let's take a look at the example. I'll call that example 1. And now we'll go to example 2. Example 2 will be the square root of negative 25. So this one is kind of different because of the negative sign underneath the radical, right? If it was out on the outside, there would be no problem. We would just bring it on down. But it's inside of the radical or under the radical symbol. So you're thinking what number times itself is equal to negative 25? Well, let's take a look at that. Positive 5, right? Positive 5 times itself. And when you're taking the square root of something, you're saying what number times itself, that sign has to be the same. So positive 5 times positive 5 gets us positive 25, but we're looking for a negative. All right, how about if we try negative 5 times negative 5? Negative 5 times negative 5 gets us, again, a positive 25, but we're looking for a negative. And we can't make these signs different because then we're not really doing what the problem says to do. The problem is saying a number times itself, the exact same number with the exact same sign times itself. So to me, there looks to be nothing that we can multiply times itself to make a negative 25. Because when we do positive times positive, we get a positive. Negative times negative, we get a positive. So there is no number times itself to make a negative 25. So for this one, we would say not a real number. And then later on, we would learn about what we call imaginary numbers, and then we would get a solution or answer of 5i. But at this point, we may not be there yet if we're just being introduced to radicals. So we would say not a real number and then move on from there. All right, Let's see. How about if we try something like this? If we had our problem be the cube root of 27. Well, what are we really saying here? We're really saying what number times itself 3 times gets us 27, right? So we can't really look at our square root chart because we're not dealing with square roots anymore. We're dealing with cube roots, right? The third root of 27. So what number times itself makes 27? So I'm thinking, as you're thinking, 3, right? 3 times 3 is 9, times another 3 is 27. So 3 is our solution. The cube root of 27, or the third root of 27, is 3. All right, let's see. How about another one somewhat similar to that? Now we're going to take the cube root of negative 64. So same situation. I'm thinking, what number times itself 3 times will get me a negative 64? And remember, in problem number 2, it wasn't a real number because there was nothing times itself, you know, to make a negative 25. However, cube roots, that can possibly happen, right? We can possibly say, okay, some number times another number times another number, even if they're all negative, that will result in a negative answer, wouldn't it? Negative times negative is a positive, and then positive times that third negative would make a negative result. So now we know that'll work, but we have to think of a number. How about 4? 4 times 4, negative 4 times negative 4 is positive 16. Positive 16 times a third negative 4 is negative 64. So our answer is negative 4. And the key thing here in me writing this example is so that you would understand why in problem number 2 it's not a real number, and in problem number 4 we do have a solution, right? Because we could create we could create a negative times a negative times a negative to make a negative answer. All right. All right, let's move on to another problem. We'll call this problem number 5. And in problem number 5, what I want to introduce here is a radical. Let's say we have some value a with the index of n, and then that radical is raised to some power we'll call m. So this is not the actual problem, more so to show you the definition and how we change a radical to a value with a rational exponent. And when I say rational exponent, I just mean an exponent that's written as a fraction. So whenever you have a radical, your radical always has an index, and as I discussed earlier, when there's nothing in the index, there's implied to be an invisible 2. Your radical has some value underneath, and it's always raised to a power. If there's no exponent there to be seen with your eyes, assume that there's an invisible 1 there. Let's say if you're 18 years old, right? So my example would be 18 to the first power. You can tell people that you're 18, and you can actually tell people you're 18 to the first power. You don't really say it or write it down like that, but in mathematical terms or in a mathematical sense, there's implied to be a 1 there as the exponent. So same thing for a problem such as this. All right, so we can rewrite this as with a rational exponent as a, and then whatever value we're raising that radicand to is in our numerator, and the index goes in the denominator. All right, so we should be able to now go from a radical to a value with a rational exponent, or go back the other way. So a value with a rational exponent and rewriting it to a radical showing the index and the exponent. So let's go ahead and try to apply this. If we have 64 to the 1/2 power, based on the definition in number 5, we can rewrite this as a radical. So know that whenever you have a rational exponent, an exponent written as a fraction, it can always be rewritten as a radical. So we can write this 64 as a radical, and then you have to say to yourself, where does the 1 go and where does the 2 go? Well, according to our definition, that that numerator that numerator is the exponent, and that denominator is our index. So what are we really saying here? We're really saying, what's the square root of 64? I know that that 1 can be written, or if I don't write it, I know it really still is 64 to the first. And when I don't write anything in the index, there's implied to be an invisible 2. So then I take the square root of 64, which is 8. If your instructions just say to rewrite it and don't evaluate, you would leave it as the square root of 64. However, that's an easy one for us, so we can look up into our square root table, and we can say the square root of 64 is 8, because 8 times itself makes 64. Alright, how about another example? Let's see if we have something like this. 125 to the 2/3 power. Alright, again, we have a rational exponent, so we can very well rewrite this with a radical. So I'll write 125, and now it's a matter of looking at our definition and saying to ourselves, okay, where do we place the numerator? Where do we place the number in the denominator? So that 2 goes either, I'm sorry, I didn't mention this, but the 2 can go right next to the 125 as its exponent, or we can place it on the outside like this. So sometimes that may be the better option, so that you can just take the whatever root it is first. So the 3 goes in on the inside as the index, and this will be much easier. So I could have put the 2 right there with the 125, but then we would have did 125 to the 2nd power, and who wants to deal with really large numbers like that, right? So you can either put it right next to the 125, or you can put it on the outside. So we can do the cube root first. So what's the cube root of 125? That means what number times itself 3 times makes 125. What number times itself 3 times is 125, and I believe that's 5, right? 5 times 5 is 25, times another 5 is 125. So we've taken the cube root, which is 5, but we still have to raise it to the 2nd power, and raising it to the 2nd power, we get 25. Right? If they say in your instructions do not evaluate, to just change it to a radical, then you would just write that 2nd step, or I should say that 1st step. But if you were asked to evaluate, you would go further, as we just did. Alright, let's take a look at a problem such as x to the negative 2nd power. So now we need to take a look at properties of exponents. So properties of exponents, and try to remember properties of exponents. If not, you can look at another video that we have on properties of exponents. It has a good summary of those rules. So we have a negative value. We don't want a negative value for our exponent. So what does that tell us? According to the property of exponents, it tells us that we need to move it down to the denominator. Right? Whenever we have a negative exponent and this value right here is in the numerator, which it is, right? X to the negative 2nd is actually x to the negative 2nd all over 1. And again, let's use a birthday example, an age example. If I say I was 25, I can tell my friends I'm 25 over 1, or I can write it down on paper as 25 over 1 as a fraction, right? And that means the exact same thing. So same thing for this one, x to the negative 2nd power all over 1. So when the exponent is negative and it's in the numerator, we bring it to the denominator. If it were already in the denominator, we would just take it to the numerator, and by mathematical property of exponents, it becomes positive. So we have 1 over x to the 2nd, and x to the 2nd, we just leave that alone. If it were an actual value like a 4 or something, we would do 4 to the 2nd power. Alright, let's try this one here, 16 to the negative 3/4 power. So it looks like here we're combining things, right? Number 8 where we have a negative exponent, and all the things we just did as far as rational exponents turning into radicals, right? So we have a negative exponent. Let's take care of that first. This is actually somewhat similar to writing 16 to the negative 3/4 power all over 1, right? So we don't want the negative exponent, so we make it 16 to the 3/4 power. We move that to the denominator, and it becomes positive based on what we did in number 8. However, now we still have the rational exponent, the exponent that's a fraction. So we want to use what we just learned and say to ourselves, oh, let's change that to a radical. 16 right there, and then say, okay, where does that numerator go and where does that denominator go based on the definition that we have in number 5. So based on number 5, it looks like that numerator, that 3, goes on the outside as an exponent, and that 4, that denominator, goes in as its index. And then we can go ahead and say we have 1 over the 4th root of 16. The 4th root of 16. So what are we saying? We're saying what number times itself 4 times will get a 16. I believe that'll be 2, right? 2 times 2 is 4, times another 2. 2 times 2 is 4, right? Times another 2 is 8, and then at 8 times another 2 gets us the 16. So 2 is our answer for the 4th root of 16, and we still need to raise it to the 3rd power because we do have that 3 on the outside of the parentheses over there. So then we have 1 over 2 to the 3rd power is 2 times 2 is 4, times it, that third 2 is 8. So there we have it, 1 over 8. Alright, so what you should do is just go over these problems and maybe search some similar problems like it and just give it a little practice. If you're not familiar with properties of exponents, you can look for the videos that we have already posted on properties of exponents. It'll be a good review for you. Alright, don't forget to, I hope this has helped you a bit. Don't forget to hit the like button, share to friends, classmates, family members who may need this, and subscribe for more videos.